I think we'll just get started. Today's presentation is on ASTRID Lessons Learned. Doing today's introduction is Patricia Padier. Patricia is the Director of the Office of Materials and Chemical Technology in the Department of Energy, Office of Nuclear Energy. She's also the Chairperson for the GIFT Training and Education Task Force. Patricia?
Yeah, thank you so much, Bertha. Good morning, everybody. It's my pleasure to introduce Gilles Rodriguez from the French Atomic Energy Commission, the center of CADARACHE, where he is a senior expert engineer. He is occupying the position of deputy head of the ASTRID Project team since 2016. He graduated from the University of Lyon in France in 1990 with an engineering degree in chemistry, and he obtained a Master of Science in Process Engineering from the Polytechnic University of Toulouse in 1991. His areas of expertise are fast reactor technology, liquid metal processes, process engineering. From 2007 to 2013, he was project leader of the Sodium Technology and Components within the CEA SFR project organization. Since 2013, he joined the CEA project on Sodium Fast Reactor, ASTRID for Advanced Sodium Technological Reactor for industrial demonstration, first as responsible of the ASTRID Nuclear Island. So without delay, I'm going to give the floor to Gilles, and I would like to thank him strongly for volunteering to give this webinar. Thank you again, Gilles.
Thank you, Patricia, and thank you, Bertha. Hello, everybody. So I will start my presentation, which name is ASTRID Lesson Learned. So the outline is the following. I will just recall or present the French nuclear policy and its position regarding the several Gen-IV systems and related coolants. That we try to explain you why we much more focused in France on the development of sodium fast reactors within the Gen-IV systems. So I will just try to explain the advantages and challenges of the sodium fast reactor concepts. And after I will make an overview of the ASTRID program and its related design, where I will try to explain you and to show you the main achievements with some drawings of the ASTRID project. And so after I will finish with my what I have put on the lesson learned regarding the development of a large and complex project and the development in particular of sodium fast reactor design. So first of all, I would like to show you the rationale for a closed fuel cycle in France. So in fact, you have to keep in mind that the trend in France is to move from plutonium mono-recycling to plutonium multi-recycling systems. And so as far as with Gen 2 or mainly Gen 3 systems, you can make some plutonium mono-recycling, like in light water reactor. In the way that you want to move to a plutonium multi-recycle system, you need to incorporate in your system fast reactors. So the thing is, we want to move from a current closed fuel cycle, but only with mono-recycling, to a future closed fuel cycle with multi-recycling of plutonium, to consider plutonium like valuable materials and not like a nuclear waste, which is very important in the way of having major resource savings, plutonium stockpile minimization, energetic independence and economic stability, decrease of waste burden and optimization of the disposal, and in such a way also public acceptance in the way that you are decreasing your plutonium stockpile. So this is a strategy that we developed in France, and you have to keep in mind that all the things that I will present is a sort of strategy that we consider within France, and in the case of nuclear energy, the strategy from France could be different from the strategy from the European community, for instance. we have a sort of independence in that specific subject. So in that case, in fact, we carried out a multi-annual energy plan, French multi-annual energy plan, which is updated every 5 years. And an update will be issued at the end of 2018. So I cannot forecast what will be the continuation, but up to now, I could say to you that the strategy is the future closed fuel cycle, and in that strategy, so by plutonium multi-recycling, the need of fast reactors is essential. So, of course, in that case, we have a reference for the roadmap based on the reprocessing of oxide fuel and on the use of fast reactors. And in that case, we make a survey of all the system, the Generation-IV system, and we take the decision to go forward with sodium-cooled fast reactors, but I will explain you on the coming slide why we make this kind of choice. Yes, so because I think you have seen a lot of presentation, you're very well known all these 6 systems that are the basis of the Generation-IV international forums. And so among these 6 systems, you have several systems which are on closed fuel cycle, so sodium fast reactors that I will explain later, gas fast cool reactor, lead fast cool reactor, and molten salt reactor, and 2 others which are open fuel cycle, but which are developed as a Generation-IV for some other purpose, and so the cycle is not completely involved in these 2 open fuel cycle systems. So the thing is we have to select because, of course, it's a huge work to work on all of this, and the purpose of the Gen-4 system is to share the work, in fact, by all the countries which are involved in the Generation-IV system. So maybe you are very well aware also of this table where you can see as column all the countries which are involved in Generation-IV forum, and on the different lines the different system, and you can see in green where there is a contribution of each country for each systems. So if you go to the 4th column for France, so we have the major input and impact on sodium fast reactors through the ASTRID project, but we still keep an involvement in some other systems such as VHTR, materials, hydrogen technology and production, on gas fast reactors with the involvement on Allegro project, and also on molten salt reactor, but in that case it's much more the CNRR, so the science department which is involved, the French science department, and not completely CEA, it's just an overview for CEA in that case. But you can see that we have a sort of matrix where we can see that we can fulfill within this matrix all the system by several countries. But of course we are not fulfilling all the countries by all the system, but it is not the objective of the Gen-4 system actually. So if I just try to present you a quick analysis of the different cooling technology which are compatible with fast neutrons. I will not say, even if we have chosen sodium, I will not say that sodium is the best. In fact, we have to fulfill with some advantages and some drawbacks. And so each of the coolant has his kind of advantages that I wanted to highlight, but also some of their drawbacks. Why we select sodium? In fact, it's a consensus because it is a mature technology in France, and so it was much more efficient for us to start to work or to restart to work, because we have already several sodium fast reactors in development in France, to restart to work with all this accumulated knowledge and gain experimental feedback. So if I'm just focusing on the coolant, of course for sodium, The major advantages are the high conductivity. It is liquid from 88 to 883 degrees Celsius at atmospheric pressure. So it gives us a large and a wide range of liquid, which is quite interesting for safety development and safety demonstration. So we have no phase change and we have a large margin before having a boiling state. Sodium has a low viscosity when it is liquid, and so high conductivity, liquid, low viscosity means that we can make some hydraulics testing, not with sodium but with water, and after we can make quite easily the transposition, which is something which is very convenient when you have to make some qualification tests, because of course it's much more easy to handle water than sodium in any case. Something which is also major advantages, and you have to keep in mind when you are using or selecting coolant, it is a compatibility with steels. And in that case, sodium is not so aggressive with stainless steel, but we can say that we have not a lot of difficulties regarding corrosion systems as we could have with lead, for instance. It's an industrial fluid, so it's quite easy, and you have a large quantity also, so the impact on the cost of the coolant will not be very important, so it was the directly line just below. We have a relatively low cost of sodium, metallic sodium, when you have to buy it. As you might know, sodium is done by electrolysis, and in fact you make an electrolysis of sodium chloride. Sodium chloride is something that you can find everywhere because it is a salt from the sea, for instance. And so the price, roughly, to keep in mind, roughly the price of metallic sodium is very dependent of the price of electricity, because you need to give power and electricity to separate sodium from chloride. Okay, so, but I have put also in orange the major drawbacks of using sodium, and you have two major about the chemistry of sodium. Sodium is very reactive because it's an alkali metal, and so it can easily react with air and with water. So we will have to deal with this kind of system by using or by developing the sodium fast reactor design. And it is one of the major drawbacks of sodium, metallic sodium in that case. And the second major drawback is that sodium is opaque, so you will need to have different systems in order to be able, an innovative system, to be able to make in-service inspection and repairability within sodium fast reactor. But I will explain it later in my presentation. And so an immediate consequences of its reactivity is that you will need a secondary circuit on the design of a sodium fast reactors. And so this is the price to pay in order to use sodium fast reactors. You will see that at the early beginning, you need to have a secondary circuit. If I'm going through the other the other coolant, so lead is considered for France as a variant. It has the advantages at the opposite of the drawback of sodium, so no reactivity with air and water, no chemical reactivity, I will say. And it is a good coolant also, it has a good cooling properties. But after, the drawbacks are corrosive, toxic, very dense, opaque, high temperature for maintenance, the density is quite high, and you can have a risk of vapor explosion in the primary circuit if you put an injection of steam inside lead. So usually you can use lead, or sometimes we are using also to try to decrease the constraints of or the drawback of these materials. Usually we can use an eutectic with lead baseness, but it will not alleviate all the drawbacks, but sometimes decrease the difficulties, mainly in toxicity and on the density. So if we deal now with helium, helium is considered in France or at CEA as an alternative. In that case, there is no temperature constraints because there is as a gas, there is no boiling temperature, okay? So no phase change. It is inert and it is transparent, so it's quite easy to make in-service inspection and repair in that case. I would say easier, not easy, but easier. But what you have to keep in mind, you will have some drawbacks also. Low density, so you will need to have a high pressure in order to be able to have a high efficiency for the reactor, because as the final goal also it's to produce electricity, so you need to think about the yield. And for heat transfer, you need to have some pressurization of the helium fast reactors. You will need to have a challenge for decay heat removal architecture with passive system. And something also you have to keep in mind is that helium is not such an abundant material on Earth. So for the deployment of this kind of system as a Gen-IV reference system, it's not so obvious because in that case we could have investigate a sort of lack of helium leading to raising the price of the material in itself. So if I'm going to the French Generation-IV program, so as told you, so French nuclear policy towards a more sustainable nuclear energy. So as I say at my first slide, it requires a cycle based on fast neutral reactors in order to have the multi-recycling systems. We want to have also the possibility for deployment of commercial fast reactors in the second part of this century. And in that case, the need of having a system with a quite high maturity is quite important. So it's the reason also of the choice of sodium-cooled fast reactors, because if we go to the maturity analysis level, I can sum up that there is about 450 years of operation in the world with sodium fast reactors, which is on the table here. I try to update this table every year. I don't know if it is exactly, but I think yes, for 2018 it's up to date. So in green you have the fast reactor which are still in operation. In white the reactors that has operated but now stopped, and in light green the reactor that has to be commissioned or will make some starting soon. So if you sum up all these dates and all these years, you achieve 450 years operating, but it's spread all over the world, so it's a real truth or a real proof that you will need to share the knowledge in order to gain from all the community the experimental feedback of the operating of sodium fast reactors. And the other system has not such a high value of cumulated years of operation all over the world. So this is, if you make a quick decision about the level of maturity and when you want to deploy sodium fast reactors, when you want to deploy fast reactors, so it comes to an evidence that you have to give a big advantages to sodium fast reactors compared to the others. And there was no implementation of lead fast reactors, of fast molten salt reactor or gas fast reactors in such a power and for such a long time. So in fact, yes, the balance is very for sodium in that case if you just focus on the level of maturity. So in that case, the French fast reactor program is the following. So the priority is given to the sodium fast reactor system, but in all his scenario, so the reactor and its associated cycle via the ASTRID project. So ASTRID will help to validate breakthroughs on cycle and on sodium fast reactors design at the same time on the same level. And we want still to make some active survey on some other Gen-IV fast and thermal neutron system through the contribution to European project, through IAEA or through OECD collaboration, Of course, through the contribution to Gen-IV International Forum, as I presented previously on my table, and also through specific collaboration frame, for instance, for gas fast reactors or for molten salt reactors. So we keep a major effort on sodium, but we do not skip the other system, and we keep survey or an involvement inside the other system as well. Yes, so this table also is just here to show you that sodium fast reactors is developed worldwide and by major countries. When I'm talking about major countries, I'm thinking about major countries involved in the development of nuclear system and nuclear reactors. So as I told you, of course, we have France and ASTRID Project. In Russia, there is BN 800, but we have also some other projects like MB or BN 1200. In China, there is a development and the operation of CEA and there is the future development of CFR 600. In Japan, there was a prototype Japan Sodium Fast Reactors, which is in standby now, but we will see that there is some link between the development of JEA on Sodium Fast Reactors and on the ASTRID project right now. In South Korea, there is a PG SFR. In India, there is a PFBR plus some other project under deployment. And in US, you have also some different projects using sodium, TerraPower, PRISM, and recently VTR, versatile testing reactor. So here again, the collaboration is under discussion with ASTRID Project and USA on the coming months. So you can see it is a worldwide development, and so the trend of Generation-IV is to try to make a mutual development between the whole system, keeping in mind that you can have your own design, but you can share also some knowledge and feedback through the different countries, as I explained before. So just to focus now on sodium fast reactor design, as you can see here, it's a simple design, and this is the kind of design we are using usually to present sodium fast reactors on the Gen-IV International Forum. Why I say it's a simple design, you can see that the drawing of this pump is very simple, and you cannot define this pump like this. You need to have an extraction from the primary vessel. But basically, you have the main function of a sodium fast reactor within these drawings. It's a pool type reactor, meaning that all the primary sodium is remaining in the primary vessels, which is separated in two parts, what we call the cold plenum here and what we call the hot plenum here. So, okay, so you have a pump which will force the sodium to go through the core for heating, going outside for a temperature from 530 to 550 degrees Celsius, and after you will have to extract this heat in order to produce electricity. And so in that case, as I was telling you, the major drawback of sodium chemical reactivity is force us to provide an additional circuit, which is here, you can see, to produce steam through the steam generator with a pump. So we cannot put and add directly steam generator inside the primary vessel because of the bad consequences that we could have on sodium water reaction in case of loss of tightness and the high depressurization of steam inside the primary vessel. So it was quite obliged by using sodium to develop an additional circuit, what we call an intermediate circuit or secondary circuit sometimes. And this additional circuit, of course, will make in such a part an extra cost compared to the investment cost of a PWR. At the exit of the steam generator, so from here to here, we could say that all this part is very conventional and there is no specific impact of this system on sodium fast reactors. So we just have to concentrate on all these systems. You have here a man, so you can see roughly the position and the size of the primary vessel. So to give you roughly an idea, for instance, on ASTRID fast reactors, the diameter of the main vessel is about 16 meters, and the height is roughly from this part to this part is also roughly from 15 to 60 meters. So you can see it's a huge vessel, no pressurized, no need to pressurize because it's very good heat coolant, but you can have in that case sort of figures in your mind. So I will just quickly recall the favorable features of sodium fast reactors. The whole primary circuit is contained in the main vessel, including the core, intermediate exchanger, and the primary pumps. The primary system is not pressurized. The intermediate system transfers the energy to steam generator, providing for an extra containment between the primary circuit and the environment. We have a very large boiling margin of sodium, over 300 Kelvin. The large quantity of primary coolant provide a high thermal inertia in case of loss of the main heat sink, and will have a very important gain on that subject according to safety demonstration case. We have a good natural convection and circulation features allow to design passive, diversified decay heat removal systems. This is also a gain that we could have, and we can demonstrate in that case that we can fulfill all the safety scenarios related to the loss of electricity, for instance. We have a power control by single rod position, no xenon effect, no need of soluble neutron poison. So in that case, we can say that the operating of the core is quite easy to handle related to PWR. And something also which is not very well known, but the collective dose on a pool type sodium fast reactor is very low compared to PWR. So it's something that it is also quite important to deal with. But in fact, sodium is making a sort of auto-radiological protection from the human being. So, of course, as I told you, we have developed some sodium fast reactors, but it's not because you developed sodium fast reactors in the 50s or in the 60s that you have developed sodium fast reactors as a Gen-4 system. Because Gen-4 system, in order to be claimed to be a Gen-4 system, you have to fulfill about different specifications and requirements, and in that case, you have to make some improvement in your design. It's the reason why when we develop ASTRID, we do not reproduce the previous reactors that we had, for instance, in France, Phoenix reactor or Super Phoenix reactor, which were operated in the 70s, 80s, or in the 80s, 90s for Super Phoenix case. Why? Because these reactors are not Gen-4 systems. They are sodium fast reactors. And you have to keep in mind that there is a big difference between what we build on the past as a sodium fast reactor design and what we want to build in the future to claim and to be a Gen-4 system. And for instance, we identify all the parts that we have some lack on the design, and we wanted to fulfill this lack, in order to be able to say that we are going towards a Generation-4 system. For instance, we had some core sodium void reactivity on the previous sodium fast reactors. We wanted to invent the safety in that case, and so we developed some or explored some development of heterogeneous cores in order to be able to decrease or completely remove the sodium void walls. As I told you also, we have some drawback about the sodium chemistry, sodium-water interaction. We wanted to enhance at the same time safety and the availability. And so in that case, for ASTRID reactor project, we developed in parallel two kinds of systems or two kinds of solutions. One is a robust steam generators, and the second one is to remove completely water and to put an additional third circuit with a Brighton cycle system by using nitrogen, pure nitrogen pressurized instead of or in place of the steam water Rankine cycle. But of course, you cannot make this just by saying, okay, we remove. After, you have to make some R&D direction and R&D works, in order to be able to demonstrate if it is feasible, and also in order to be able to raise the level of maturity of this new system, which were not developed in the 80s or 90s before the ASTRID project, in the case of the French Sodium Fast Reactor development. We wanted also to develop or to improve the demonstration of safety regarding sodium fire, and so we developed a lot of innovative sodium leak detection systems in order to be able to quickly detect the tiny leak of sodium we could have and to make a sort of quick interventions in case of the indication of a sodium leak. We have also to manage the R&D about the sodium aerosols in order to make a protection from the environment, and in case of a large scenario, safety scenarios with a large and spread sodium fires, to demonstrate that we can protect the environment from sodium aerosols. We have also to develop a lot of demonstration regarding the safety and regarding the severe accidents, and this line was mainly a line and a kind of development that has been greatly increased due to the Fukushima event. So we developed a core catcher, and we make some research on corium and sodium-corium interaction in order to be able to demonstrate that in the scenario of a total melting of the core, in that case we have a quick draining of the mixing of core with sodium, what we call the corium, down to the core catcher with no primary energy excursion. We have also to demonstrate the ability of the decay heat removal in any case scenarios, and so in that case we have to make a combination of the proof decay heat removal system, and also to see that this kind of system or all of the system can find a solution to operate either in forced convection or also in natural convection in case of an unprotected loss of electricity or station blackout, for instance, long-term station blackout. And for in-service inspection and repair, which is related to safety and availability, in that case, we'll have to demonstrate that we are able to inspect in all the system and in all cases the different parts which are suspected to be able to evaluate or to have some cracks or failure. So mainly the weldings, which are the major part where you can encounter cracks and failure with time. So I will now move to the ASTRID program just to explain you what it is and how it works, and after I will show you different figures and different drawings of the ASTRID project as it is drawn now. So ASTRID is considered as a technological demonstrator, so it's not the first of a kind of a commercial reactor, meaning that in that case, because it's not the first of a kind, we still have the opportunity to incorporate some innovative technology and to raise the level of maturity of this innovative technology within the ASTRID reactor in operation, which is not the same constraint when you have a first of a kind, where the level of maturity is in such a way quite high because you are in first of a kind of a commercial reactor, so you are closer of a commercial reactor. So the development of the program is based on the feedback experiences on fast sodium cool fast reactors, and we have to demonstrate in the ASTRID case the scale allowing the industrial extrapolation, the relevancy of performances of innovation in particular in the field of safety and operability. So we have to demonstrate that what we'll demonstrate on ASTRID could be extrapolated for future large-scale and large-power commercial fast reactors. And we have also a big connection with the R&D facility to test and qualify innovative safety design, to qualify different fuels, so we can change the core by time or maybe make some experimental fuel assembly, to obtain the necessary data to justify the useful lifetime of 60 years for future sodium fast reactors. So just to demonstrate that stainless steel in major parts can fulfill the 600 years lifetime in contact with hot and metallic sodium, liquid sodium, and to confirm performance of innovative components and to establish a reference for sodium fast reactor cost assessment for the building and operation, not only for the cost investment, but also with the planning and the price for operating the reactor. So one of the targets is to say that the technology of ASTRID allows to have a very resilient design to external events. And this was an impact of the Fukushima event, but even before the Fukushima event, we had to take into account this kind of external event. So, of course, earthquake, flooding, loss of power, airplane crash, etc., etc. I could put also malevolence, etc. So this is an impact that was not so important and so major in the 80s or on the 70s. I will not say that it was not taken into account, but in that case, the number of scenarios, the number of questions has raised a lot compared to the previous system developed previously. So just to recall you the project organization of ASTRID, as you can see, we have here the ASTRID project team, which is located in Cadarachecenter. We have some assistance from EDF and a relay also at Marcoule site. And after, we are working by work package. One is on the reactor core, where CEA is responsible and Framatome is in support. One is a nuclear island with a big involvement of Framatome, also a big involvement of JEA, MFBR, Mitsubishi Heavy Industry, and SEIV for the hot cell. Another work package is on the power conversion system, and in that case, this was leading by General Electric. Another work package on civil engineering, leading by Bouygues, and another one on balance of plant and infrastructures, which is led by Knox company. And we have also some cross-cutting use or development by different partnerships, Toshiba, Volanc, NIM, Onet, and Technetics, which are for the search for innovation. And if this kind of innovation are incorporated, in that case, I will go through inside the nuclear island development. On the left part here, you can see that we have also a strong support from the R&D field. So, of course, this support is on the major brick done by R&D carried out at CEA, but also on some international or European R&D development, a project called ARDECO by EDF, the French electrical supplier, and also with important collaboration with JEA, MHI, and MFBR in the R&D field. So you have a close relationship on R&D and the organization, and in fact I will have to put an arrow because all this R&D will fulfill the innovation and will be implemented if they are accepted within the nuclear island design. Yes, I will not go in detail of this slide, so you can see that there is, of course, a lot of partnership organization that you can see with countries, with organizations, and with companies. So here on ASTRID project, in fact, we were working all together with 14 companies here, industrial companies. And these industrial companies are really industrial partners. So we have not to consider them as subcontractors or contractors. They are considered as partners. So in that case, they have the right to, we claim for them to give their opinion, to give their feedback, and so it's kind of exchange. And of course, we have after to define the work to carry it out all together, but it is not the conventional commercial relationship that we are carrying out or with all the partners. So in that case, after we have some international cooperation, but it's much more focused in that case by the R&D teams compared to the ASTRID project. I don't know if I told you, sorry, I'm going back on the previous slide. So yes, here the ASTRID project team organization is about 20% belonging at CEA. All of them are in CADARACHE, and the contracting authority here, the strategic management, is carried out by 2 persons which are located in Saclay. So in fact, it's the program department in that case. And as you have seen, of course, we have to develop a lot of R&D and innovation because, as I told you, the previous sodium fast reactors we developed for Phoenix or Super Phoenix, in the case of France, were not Generation-IV systems. So to achieve to get a Generation-IV system, you need to have some innovation and development. And when you need to have some R&D, development, innovation, in that case, you will need to have to test some systems. So, of course, modeling is making a great progress now, but in any case, at the very end, you will need to validate your modeling. So, computing codes are helping us a lot, but at the end, in any case, you need to have some experimental platform to be able to be sure that either your system is fulfilling the requirement, is making the good results, or even that your computing code is giving the good results when you compute it. So it's the reason why you need to have, in support of a design development, a large, wide, and scope of experimental platform that we develop either at CEA or sometimes we have to also to exchange with some other countries for large sodium platform. For instance, in Japan, we consider that we can have some large sodium loops in some other foreign countries. This is very important because the price of an experimental platform is quite important, and here again, the international share is something that we have to keep in mind. Otherwise, if we want to have the development of all the systems in parallel and independently, it will be very costly, and it's not the way that we are developing cost saving in other countries in that case. And this is a strategic point that you have to keep in mind. So as I told you, because we wanted to put innovation, we put a lot of digital in the ASTRID project for the design, for the computing. So sorry for the design, for instance, here. Sorry, I didn't have the green arrow anymore. I don't know where it is, but okay. I will continue anyway. For the design here, for instance, for the assessment of performance, and also, thank you, Bertrand. And also sometimes to make some meeting, because we have a complex project where we have to rule 13 partners and over 500 participants spread out all over the world, and you have to share the knowledge, and sometimes it's not obvious. So you have also to deal with this kind of situation, and the use of digital is also something which is very important in project management. In the design, for instance, you can have a lot of modeling that you can do now by performing and by computing code, and we give a big enhancement of the presentation or the demonstration for the decay heat removal system, for instance, and for the modeling. So here we have a major gain, but as I told you once again, even if we have major gain on computing code, you will need to validate this computing code, and in one time, you will need to have some experimental feedback validation for the codes as well. So you have to keep in mind, the performance of the computing codes is helping us in saving money in the development of experimental tests, but not in a way to go to zero test. It's impossible. You will need on any time to validate your code, and this is done by experimental feedback. You cannot avoid this. So less experimental, but no zero experiments. As I told you, we have also the management of a large complex project with a lot of partners. We have to exchange data for them. We have to exchange the organization, which is based on an engineering system approach, sorry. And so we decided to develop a plant life management in order to be able, not yet shared amongst all the partners, but within the ASTRID team to have an online surveillance and online following of the project by a plant life management. And of course, after we are developing something which is very well known and used now, like 3D numerical model and configuration management. You have some data here. We have over 15,000 interface data to look after for all the partners. So this is a major point of importance and of worry within the ASTRID project team in order to be able that we can share all this data by all the team at the same time. We put also some effort about the promising development of the use of virtual reality because we think it works to be able to see in 3D what will be the future and when we can handle the system. And this was much more focused because we had much more constraint regarding the operability of the system. So this is something that we take into account early in the design of the reactor, the project. So the main achievements for 2015 are the following. We had made a synthesis to the government at mid-2015, which allowed us to move towards basic design period from 2015 until the end of 2019. So now we are deeply involved in this basic design phase, and we present our main achievement at the end of 2015 on the preliminary design, which allow us by the government to go forward to the basic design system. And all the partners have accepted to continue this kind of adventure with us on the basic design phase, except one partner. Otherwise, the others say, okay, we continue with you as a partnership until 2019. So I would just want to recall now the main technical choices we started to use and to decide at the early design of the ASTRID project. The power reactor was 1,500 thermal megawatts, that is to say roughly 600 electrical megawatt reactor. As I told you, it was a pool type reactor. You have another concept which is called a loop type reactor, but we do not continue this kind of design. Of course, it was designed with an intermediate sodium circuit. Even if we want to alleviate it, we could not find any easy solution to try to remove this one. So it's a cost important decision because we know it will be more costly than PWR. We have a CFV core, which is a core with a low sodium void worth. So we put innovation here. The oxide fuel is UO2 PuO2 system, which is in coherence with the fuel management in France. We have a preliminary strategy for severe accident with an internal core catcher with the design of no large mechanical energy release. So a sort of scenario where when we have the corium, we want to quickly drain it down to the core catcher in order to be able to, or to prevent from a big primary phase excursion. We wanted to demonstrate that we can have the diversified decay heat removal system to be able to freeze or to cool down the reactor in any case situation, in case also for long-term station blackout, for instance, which is one of the major difficult systems to demonstrate because you will have only a natural convection system in operation in that case. And also we have a fuel handling in sodium with a combination of internal storage and small external storage, which was devoted to design an increase of the availability rate. So some drawings now. So just here to show you that here you have the reactor, but in fact it's a small part, as I told you here, it's a 15 meters diameter, and you can see that all the nuclear island here is quite large with very high height here, and also you will have some secondary circuits on the two parts of the belong the reactor. In case of ASTRID, in fact, we have three secondary circuits. Sorry, four secondary circuits. So this is the drawing that we have carried out with the steam water power conversion system. So you can see, not exactly, but it's here behind you have the steam generators, or you can see here on the building the steam generator systems. We have drawn in parallel another system, so here it remains roughly the same, but we have to adapt the secondary system here to be able to put some gas conversion system, and you have here 4 sodium gas system heat exchangers per loop, and after you have the Brighton cycle here, which is in the turbine hole. So we have in fact developed today in parallel at the preliminary design stage and two systems, one with steam water and the other one with pure pressurized nitrogen. So this one is another view about the nuclear island, where you can see that we have the reactor hole here, a polar table here to prevent some risk assessment and the falling down of a big component on the roof of the reactor. You have here the reactor block, and you have here the very basic drawings of an anti-seismic raft, so to prevent about the earthquake event. On this drawing, you can see the fuel handling route. So this is the fuel handling route for the fresh fuel, but if you're talking about burnt fuel, it's the opposite one. So for the fresh handling route, you go from 1 to 4. So first here, after you put it for sort of thermal consideration, and after you go through this corridor, you will put it on the extra vessel storage tank, and through a ramp you will go and put it inside sodium. For the burnt fuel, you will go exactly on the opposite way, except that here you will have on the internal vessel a decay heat system, then another additional, if necessary, decay heat inside sodium here. After you will go to cleaning and washing before making the store for the final decaying into the water pool. Something which is very important that I have to focus. As we have started to work on the ASTRID project, we decided to give at the beginning, early beginning, an implementation position of the reactor, which was located as a scenario in Marcoule, in order to be able to have the complete difficulties of all the project. Because when you are drawing this, or when you are drawing this, if you are doing the drawings without the environment, in that case, in fact, the feedback of the cost evaluation that you will do on your reactor is false, and sometimes you are giving some hypotheses which are favorable. So we wanted to be able to have the hypothesis on the real case, and it's the reason why we put the Marcoule area in order to be able to design and implement all the reactor structures to evaluate the balance of plant and the constructibility. And sometimes you have some constraints on the design of the nuclear island which comes only due to the crane, because you cannot implement your crane to design or to build what you wanted to design. So it's very important to go to the very far and the very end of the basic project in order to be able to have all the constraints at the early beginning of the design, and it gives you much more constraints, but for the future it will give you much more assessment that your reactor, your project is feasible, and you will have a much more up-to-date schedule and cost estimation. So you can see here the balance of plant as we have drawn it at the end of 2017. We saw the nuclear island, which is here. Here is the building for the fuel handling system in light red or light pink. You have here the two buildings for the gas cooling system, so one here and one here. And here is the cooling system that we replace the big cooling tower by a small cooling system in order to prevent from the view of these large cooling towers from far on the Marcoule site. And so you can see, for instance, to operate this kind of balance of plant, you have to take into account that you are close to a river, that you have to go through and to break a sort of mountain or hill here. And so it will give you some constraints that you will not imagine if you have not, at the beginning of your design, the site or an example of the site to be able to perform and to design completely your reactor in the frame of the balance of plant. And so I have to focus on that point because I see a lot of sometimes projects where there is no balance of plant, sometimes the cost estimation that you will provide is largely underestimating the real cost estimation that you will have to fulfill in case of the balance of plant design. So just going now on my slides of the lesson learned about the sodium fast reactors and mainly on the ASTRID project. So I think I have two slides. Yes, that's right, I have two slides. So the first one, which is much more general, and just to recall what I presented to you. So nuclear energy is a well-proven source of large baseload electricity with no greenhouse gas emission, and it will remain one of the pillars of the future French low-carbon energy mix. So as I told you, we make a 5-year plan. This 5-year plan will end at the end of 2018, and we'll have, it's under discussion right now, to discuss about the future 5-year plan for the 5 years to come. So for us, the closed fuel cycle, when I say us, so okay, it's CEA or France, okay, associated with the fast neutron reactors will lead to a drastic improvement of uranium resource management and important reduction in the footprint and radiotoxicity of the final waste. And moreover, of course, we are using and making the multi-recycling of plutonium, so you have a sort of combination of the work and the handling of strategy of PWR and strategy of fast reactors, which are very close and very coherent altogether. So as I told you, the French program of Generation-IV is based on ASTRID program. Basic design phase is ongoing from 2016 until 2019. Schedule and organization for the next phases are under preparation, so over 2019. And we had to investigate one option that could be to review the power of the demonstration reactor. And this was due to first feedback of the cost investment of the reactor with some constraint given by the government, with some asking us to decrease the cost investment of the project. So one idea was to reduce the power, but all the innovation of the drawing remains roughly the same. And we make also an active survey on the other Gen-IV fast and thermal neutron systems in parallel, as I present you at the beginning of my course. So another slide about lesson learned that I want some message I wanted to pass through this presentation. As I told you, sodium fast reactors is a mature technology because many sodium fast reactors were built from the 50s to the 70s, and then were operated. But the gap to achieve a Gen-IV system is significant because Gen-IV is requiring improvements mainly in safety, operational, and economic aspects. And it is impacting the related design. So it is not why you are working on sodium fast reactors that you are designing Gen-IV system. And you need to have all the expectation of Gen-IV or the requirements of Gen-IV and to incorporate them inside your design, which is a very crucial point. So even if it is a mature technology, the sodium fast reactor technology is not obvious because you are not dealing using sodium as a coolant at home or nuclear or in some other industry. And in that field, the knowledge preservation and transmission to the coming young generation is also a key challenge. And if you want to keep it, if you want to keep this key technology available for decades, which is the ratio of time for nuclear projects, you will need to have a sort of knowledge preservation and transmission strategy in parallel of your development. And the use of sodium as coolant, as for the other liquid metal or helium coolant, needs course, practice, skills, or presentation through webinar as I'm doing it right now. And innovation also is a way to design new reactors. And I'm not doing innovation for the pleasure to make innovation. I'm making innovation to fulfill the Gen-IV requirement, to fulfill the new safety demonstration that we need to have, and also to fulfill the cost investments that I have to reduce. So to make this kind of innovation, it needs to get a close relationship between industry and design teams in one hand, and the R&D teams on the other hand. And this was the role of the ASTRID team project, to make them learning together and to be able to exchange the data and to put them on the same way of understanding each other. And the sodium fast reactor design cannot be achieved without international collaboration, and I am sure of this, mainly to mutualize technological platform and infrastructures, because these kind of platforms are very expensive, and in that case, if you can mutualize them through some international collaboration, to my opinion, it's a win-win cost-saving approach that you will need to have in order to be able to develop such an important project development. Okay, I think I have been through all my presentation. Thank you for the audience. I'm open for question and answer if we have some time.
Thank you, Gilles. Thank you very much for your presentation. If you have questions on this webinar presentation, please do go ahead and type those into the chat pod now. And while we're waiting for questions to come in, we'll just take a look at the upcoming webinars. In August, we anticipate a presentation from Dr. Ricove on the Brest 300 lead-cooled fast reactor. In September, a presentation by Dr. Alemberte on the Advanced Leaf Fast Reactor European Demonstrator, or otherwise known as ASTRID Project. And in October, a presentation from Dr. Amirable on the safety of Gen-IV reactors.
Okay, thank you. That's all.
So there are a couple questions that have been entered into the chat pod, and if you roll your mouse over the Q&A pod, you can see those two tabs. One's the presenter and one's a participant view. If you look at the presenter, do you see the questions?
I don't see any question up to now, but a Q&A window, but nothing. I hope it was clear anyway.
So to the right of where it says Q&A, roll your mouse over. There's an icon of someone with a computer monitor and then just a person's head. Click on the one with computer monitor. Do you see those? There's a question that's from Skutu Gande that says Russians seek to develop nitride fuel for their sodium-cooled fast reactors. Which is a better fuel, UO2 or UN?
Oh, so we're not using nitride fuel up to now, but only oxide fuel, because in fact all of our facilities are based up to now on oxide fuel. So all our facilities for the fuel handling and for fuel process fabrication are devoted to oxide fuel. So this is the reason why we were using oxide fuel. It's very I can give you some other explanation later by the comparison between nitrile fuel and oxide fuel. But here the choice was not very difficult to do. To make an additional fabrication with some other process, it was such a big involvement in terms of time and money that we select our historical fabrication process, in fact. But I'm not giving you a clear answer about this, but the comparison of nitrogen and oxide was not done in that case. But okay, I can give you some other comparison. And once again, the comparison I've done and the position I've done on coolant, there is not the best coolant, there is only advantages and drawbacks on every coolant. I think it will be the same for the fuel, either metallic, nitride, oxide fuel. You will find some advantages and drawbacks, and after you have to deal with them. So you take the advantages of the positive features of your fuel, and after you have to deal with your drawbacks. Okay, thank you, David.
So that's, I don't see other questions coming in. There are thanks and accolades. We have time for maybe another question if there's any questions in the audience.
Okay, so otherwise I hope you enjoy my presentation. I tried to do my best to get rid of my French accent, but it was not obvious anyway. And if you have some additional questions, please feel free to send me an email. I think you get my email on the presentation, so I can have a online answer done afterwards.
Exactly. Thank you very much.
Yeah, thank you, Gilles. It was so interesting.
Thank you very much.
Bye.
Okay, have a nice day.
Okay, bye everybody. Have a good day.
Okay, bye-bye. Au revoir.